Hi Rockers, this is Mrs. Berger, and this lesson is for the Algebra 2 students that are taking probability and statistics and discrete math next year. So you should have gotten through your warm-up, working with your partner to come up with how strongly associated your food preferences are. And when you draw conclusions about how correlated you are, how associated your food preferences are, you should have a statement something like, our food preferences are either positively or negatively associated. So we would or wouldn't, depending on your results, enjoy going out to eat, enjoy eating out together. Okay. The point of this being, this entire class, probability and statistics, and then the second semester of discrete math, going out to eat together, is about interpreting the math and about applying the math to a scenario. And so we really want to get you to make that connection between the numbers and the data and what's actually happening in the real world. So you'll hear me talk a lot about the phrasing and how things should be phrased and how important the phrasing is. Okay, so that was just a little intro into that. So let's roll right into the notes. In statistics, when we have these pieces of data where we're comparing one variable against another, we talk about correlation. The value of correlation, or somebody telling you the correlation is some number, that they're telling you two things at once. They're telling you about the strength and the direction of that relationship, of a linear relationship between those two variables, those two quantitative variables. And correlation is always going to have a value between -1 and 1. If your data is trending downward, R is going to be a negative value, and your variables are negatively correlated. If the data is trending upward, as one variable goes up, the other variable goes up, R is a positive value. The two variables are positively correlated. If there's no correlation at all, and this may have happened in your example, you may not be good dinner partners at all if you had zero correlation. If R is 0, there's no correlation between the variables. And so this closeness to -1 or +1, that is how you measure strength. Okay? So if you have an R value of -0.99, that is strong negative. Okay, that correlation value, R, is a strong negative relationship between those two variables. If you have an R value of +0.6, those are moderately positively related. So those two values, the moderation or how strong it is, as well as whether it's positive or negative, is what you get out of that R. Okay. Now, a regression line, and what its common use are, is a regression line is a line that describes how a response variable, and remember response variables are Y variables, so response or Y variable changes as the explanatory variable, explanatory or X variable, changes. And again, the wording here is really important. This line, this regression line, or this line of best fit, is a line that talks to you about how these two variables are working together, or working against one another. So how is the Y variable changing as the explanatory variable changes? Okay. Its most commonly used to predict values outside the interval of actual data. Okay? So if you collected a bunch of data and you fit a line to it, you fit a line to that data that you collected, and then you try to make a prediction about data that, or an event that might happen outside the original data collection. Remember what that was called? In Algebra 2 we talked about this. It's called extrapolation. Alright, now the format of your regression line. It's going to be slightly different than the types of lines that you've seen in algebra, just a little bit of different order, okay? And this again is very important. The order of this is very important. So when you have a regression line, when you put in a bunch of data in your calculator and you find the curve of best fit or the line of best fit, you'll have y hat, that's what that little thing is called, y hat, equals a plus bx. Now you'll notice that this is similar to y equals mx plus b, just in a little slightly different order, and that's because we find importance in a starting point in a y-intercept, okay, and that's why this is the format that it is. But let's break this down. What do we have here? Well, like I said, this is called y hat, and y hat is the predicted value of y, or the response variable. Okay, that's the predicted value of the response variable. Remember, this is just a line of best fit. This is not an actual piece of data that was collected. This is just what that y value is on the line of best fit. So this is what we use to help predict things. This isn't what actually happened in our measures. A, that's our y-intercept. And so that's the response variable's value when x equals 0. And sometimes that y-intercept is going to mean something in the context of our problem, and sometimes that y-intercept is not going to have any basis in reality and is not going to be useful, and you'll see that. B is the slope of our regression line. This predicts, or this is the predicted change in y for every 1 unit change in x. And the wording of that is very important. In order to interpret a slope in context, you'll take that number, whatever it is, maybe it's 2, maybe it's 0.3, whatever it is, and you'll say, this is how much we predict the y will change for every 1 unit change in x. And of course, x is your given x, whatever input you're talking about. Okay? So the wording of that is super important. If you need to pause the video and make sure that you get the wording of these, please do so, because that's how you'll be answering these questions on quizzes and tests. Alright. What's the least squares regression line? Quite simply, this is the line of best fit. You guys have seen these before. If you are on your TI calculator, TI 83 or 84 calculator, in order to use your calculator to get a least squares regression line, what you'll do is you'll go to Stat, Edit, and then you'll enter your data in List 1 and List 2. Then you'll do a Stat Calc, and you'll choose a linear regression, and you'll use the a plus bx form instead of the ax plus b form, because in stats that's the form that we like to talk to things in. And then we also want to make sure that we remind you, go into mode and turn stat diagnostics on so that you'll get that r squared value. Okay? If you need to take a minute to reorient yourself with the calculator, please do so. Alright, so when we run these stat diagnostics, when we run these linear regressions, we get a couple of values. We get a value for r and a value for r squared, and we need to understand what those values mean in context of our problem. Okay? Once again, r is our strength and direction, like we talked about at the beginning of our notes. Okay? This is the strength and direction of a linear relationship between your two quantitative variables. And we need to contrast that, compare and contrast that, with what r squared is. We're going to keep this definition simple for now. R squared helps you measure, or that measures, the percent variability in the response variable that is accounted for by our least squares regression line, or our line of best fit. Okay, and again, the wording is important. So r squared, when you translate that in context, if somebody says, if your calculator says r squared equals 0.87, that means 80% of the variability in your y variable is accounted for by your least squares regression line. Okay, and in layman's terms, it's how well the regression line makes predictions. And if you can't tell already, probability and statistics is definitely heavy on the words and the notes. Okay. All right, so before you try these problems on your own, I want to do some group practice with you together. Okay. So let's pull our calculators out and take a look at this first problem about a statistics student who wonders if tall women tend to date taller men versus short women. And so our explanatory variable, or our x value, or our list 1 variable, is how tall the women are. And our response variable, or our y variable, or our list 2, is the height of our men, and how the height of the man that the women date. So let's go ahead and put this into our calculator. Go ahead and pause the video if you need to, and put that in stat, edit, list 1, and list 2. All right, so we have our data entered here. And now we're going to fit a line. So stat, calc, linear regression, and we're going to choose choice 8 because we like the format in statistics of choice 8. And all of our data is in list 1 and list 2, so we can leave the defaults. And we calculate. And what our calculator is telling us is that the least squares regression line is y equals 24 plus 0.682x. So we'll start answering these questions by documenting that. So we're going to use our technology to calculate the equation of least squares regression line. Let's just jot that down. Y hat equals 24 plus 0.682x. Now, we are nowhere near finished answering this question. In statistics, we've got to relate our results to reality. So let's first start by translating these x and y values into what actually this means in the real world. We are trying to predict, the y hat represents, height of the man that she's going to date. So the predicted height of the man, you put a hat over top of that, equals 24 plus 0.682 times the height of the woman. That's what that equation means. We never leave them in x's and y's. We always get them into context as soon as possible. Now, interpret the slope and y-intercept. So we know where the slope is. The slope is right here. And so let's interpret this. And please pay very close attention to the wording here. To interpret that slope, what we say is, for every 1 inch increase in a woman's height, the predicted height of the man she dates increases by 0.682 inches. That is the proper interpretation of that slope. Okay, so first you need to identify where the slope is, then you need to interpret it in context. Next, we'll interpret the y-intercept of that line. We know where that is, right here. That's your y-intercept. And we need to think about what it means to have a y-intercept here. The y-intercept happens when x is set equal to 0, right? Well, what does that mean in context? What is x? X is the height of the woman. Is there such a thing as a woman that is 0 inches tall? Absolutely not. So in this particular scenario, the y-intercept has no meaning. If we could possibly have a 0-inch height woman, we would interpret it as when a woman is 0 inches tall, the predicted height of the man she will date is 24 inches. However, we would not put that phrasing down for this because there are no 0-inch tall women. Okay? So that's how you answer this question, does the Y-intercept have meaning? Always check for whether it has meaning before you start interpreting it. There's no reason to interpret something that couldn't possibly happen. Okay? So that is very important. Calculate and interpret the correlation of these data. So our calculator, since we had stat diagnostics turned on, they went ahead and gave us an R value. And this R value turned out to be 0.57. So let's interpret that. Calculate and interpret. So our calculation reveals 0.57 for our correlation. And to interpret that, we say the linear relationship between height of women and height of men they date is moderate, because that R value of 0.57, that's a moderate value. It's not terribly strong, close to +1. So it's moderate, but it is positive. So and positive. So we've proven that, moderately speaking, the taller a woman is, the taller the man that she chooses to date will be. But it's not a very strong correlation. It's a moderate correlation between increase in height of women and increase of height in men that they date. That's the wording that you will use to interpret an R value. Calculate and interpret the coefficient of determination for these data. Remember, that means R squared. Coefficient of determination is R squared. And for us, that R squared value is 0.32. So we'll go ahead and calculate it by saying R squared equals 0.32. And to interpret it, we'll say 32% of the variability in height of in predicted height of men is accounted for by the least squares regression line. Okay, that is the verbiage you'll need to use when you interpret an R squared value. Again, statistics is not something where you just tell me, Mrs. Berger, R squared equals 0.32. You need to interpret it. Always calculate and interpret. That's our instructions for almost the entire class. So you'll say 32% of the variability in the predicted height of men is accounted for by the least squares regression line. Okay? So keep these notes handy as you do your independent practice to have the wording down. You'll just need to switch out your variables depending on your scenario. Let's do 2 more questions. They're multiple choice questions. If we've got a situation where there's a positive correlation between the size of a hospital, basically how many beds they have available, and the median number of days that patients remain in the hospital, does this mean you can shorten a hospital stay by choosing to go to a small hospital? And what we want to highlight here is that just because 2 variables are correlated does not necessarily say that you can draw a conclusion about causation. Okay? So just because the bigger hospitals tend to have patients that stay longer, that doesn't mean that if you go to a small hospital, you'll shorten your stay. We really are just trying to use our vocab to talk about the fact that correlation does not imply causation. So the answer to this question is no. The positive correlation probably arises because seriously ill people go to larger hospitals. And you tend to go to smaller hospitals if you just have a small injury and you won't stay very long. So just because something has a positive correlation does not mean that one variable is causing the other. Number 3, In a certain population, there's an approximately linear relationship between the height of females in centimeters and their age, described by the equation y hat equals 50.3 plus 6.1x. Which one of the following statements is true? And again, this is using our verbiage, our wording in statistics to interpret this equation that's spit out of somebody's calculator. So estimated slope is 6.1. Yes, I like that. This implies that girls in this population between the ages of 5 and 18 are predicted to grow about 6.1 centimeters in height for each year they grow older. I like that sentence. It looks like a winner so far. Let's look at the rest. The estimated intercept is 50.3 centimeters. We can conclude from the intercept that the typical height of girls in this population at birth is 50.3 centimeters. You might be tempted to like this statement as well, because when x equals 0, y equals 50.3. However, notice that they said this data came from people who were between the ages of 5 and 18. 5 and 18 years. It did not include, this data does not apply to people at birth. So that one's out. C. A 10-year-old girl in this population is at least 110.3 centimeters tall. We don't love the wording of this. A 10-year-old girl in this population is at least 110.3 centimeters tall. Remember, this is a prediction. So we need to be saying, we predict a girl between the ages of 5 and 18, when you enter their age in years, between 5 and 18, the predicted height would be 110.3 centimeters tall. So we don't love the wording of that one. And then finally, one particular 8-year-old girl is 115 centimeters tall. She is shorter than expected for girls her age in this population. If you were to input an 8-year-old girl, her age of 8 years, into our prediction formula, you would get 104.7 centimeters. The expected height of an 8-year-old girl would be 104.7. If one particular girl is 115 centimeters tall, she is taller than we had expected. So that's why that one's out. We love the wording, we love the interpretation. A is our choice. So again, focus on your wording and go ahead and try your independent practice.